And then what is missing? So open neutral, open ground, or open hot. And using your meter, it's very easy to determine which one is missing. One of the things that you want to do with an outlet is double tap, check twice, check between hot and neutral, all right, in all cases, and then check between hot and ground. So that's how we're going to set this up. We're going to do a double check, hot neutral, hot ground. And this is why if you take nothing away from troubleshooting, hopefully you take more than this one thing, but if you take nothing else away from troubleshooting, take this with you. See the problem in front of you. Don't just take someone's word for something not having power. All right? Because people will say a lot, this is not working. That has no power. I plugged in my lamp and my lamp is not working. That has no power. And once you start to just kind of go, well, that has no power, and then you plug in the lamp and you're like, yep, that has no power. All right, let me check to see what happened to the power, and let me go to the breaker. We want to get a visual of what, quote unquote, no power means. All right, so if somebody was asking, I think the mic went out in there. If you guys go quiet, the mic kind of shuts down, so give it a second if you did ask a question. Once somebody moves something, the mic kind of goes on. It's just a thing that it does. But so we want to know, what does that mean? If the lamp isn't working, what does it mean by no power? So let's do first open neutral. So open neutral is going to have 120 volts between the hot and the ground, but it's going to give you 0 volts between the hot and the neutral. So if you, for example, if you head over to this outlet to check because the lamp wasn't working, and you put your meter on one side, the bigger side is always the neutral, and then you put it over here, and your meter says 0, and you're like, well, there's no voltage at the outlet. Not so fast. Check that hot to ground as well. Because now, if you check the hot to ground and there is 120, then it actually means the hot is here, but the neutral's not here. And that's a different problem. The hot not there, that's a problem in one direction. Check breakers. Somebody earlier, by the way, good thinking, I believe it was Mr. Lindsay, who said, I don't see GFCIs. Very good. We're in a kitchen. That is a good thing to keep in mind. If I'm in a kitchen and I don't have power somewhere, before I go to check the breaker, let me do a quick scan and see if there's a GFCI that's tripped. All right, easy first, then we go down the road. That's why for continuity, no, not yet, because continuity requires taking things apart, getting up in attics sometimes, going to grab ladders, tools, etc. Not that we don't do that, but we try to go to the easier routes first before we start to get into deeper waters. Most common problem, if something is not working, is either no hot or no neutral. Open ground, yes, this is important. Absolutely. And by the way, I put negative here. I don't want to do that. Yes. So it's just the reverse when we have an open ground. We're going to have 120 between the hot and the neutral, and then we're going to have nothing between the hot and the ground. But I'm going to use it for a reason. And then open hot, you're going to check between the hot and the neutral, 0 volts. Wait a minute, is it no hot or is it no neutral? Now we'll check between the hot and the ground, and then we'll have 0 again. That's just telling me that hot and that ground, that hot is not available with either the neutral or the ground. All right, good so far. Now here's a fourth problem that could happen, and that is reverse. When things get reversed. Now, there are two ways that somebody can reverse things in a device. One of them is almost a non-issue, and that's when somebody reverses the hot and the ground. This is going to present a short circuit. Either when you plug something in or when they mount it onto the box and turn the breaker on. If there's a ground and it's grounded and the ground is heading back to the panel and you have the ground on the hot side and you have the hot on the ground side, then it's going to short something out. Something will pop on the breaker. Or if it's a GFCI, it'll immediately just trip. So a lot of times the reversed hot and ground is not necessarily something that you're going to find or need to look for. The one that's more common and sometimes goes completely unnoticed is the hot neutral reversed. All right, and I'm actually going to put it here. Hot neutral reversed. And the reason I'm putting it there is because it looks exactly the same. Think about it for 1 second. If I were to land my hot conductor on the neutral, and I was to land my neutral on the hot, and I plug in my tester, which is dumb, right? It's not thinking through this, and it goes this way and this way, what's it going to read?
I'm sorry?
What's the meter going to read in this case if I have the hot on the neutral and the neutral on the hot? And I put my meter into the hot and I put my meter into the neutral slot. What's the meter going to say?
120.
120. If I then go hot to ground, guess what the meter is going to say?
0.
0, because the hot's sitting over here. So I have to do a third test. What's the third test?
Neutral, ground and neutral?
Ground to neutral, very good. Nice, took a second, but you thought in the right direction. Exactly, I want to check now between the neutral and the ground. So I'm going to put it down here, neutral, ground, and this is now going to read
Negative something. I don't know.
120. It's going to read 120 because the hot's sitting here. I've got my neutral over here, and of course the ground didn't change. So when I check between hot and neutral, I got 120 because there is a hot and there is a neutral. They're just in the wrong spot. When I check to see how's the ground doing, and I check between what I consider is the hot side of this outlet and the ground, I got 0. So now I'm thinking, oh, well, there's no ground. Can't happen. But I do the third test now. And the third test is, as you said, between the neutral and the ground. And now, wild, it's going to give me 120, which should never, ever, ever be the case. The neutral and the ground should have 0 on it. And so that's what we determine now. So I'm going to connect these two. Make sure you write it as a fourth note, to this setup. If you need it, if you already got the comments, I already understand this. When I have no neutral, when I have no ground, I know what that looks like. Technically the opposite of each other. And then of course 0, 0 with no hot. Make sure you also understand hot, neutral, reversed. Now this is where the plug-in tester becomes our best friend. Just you're plugging in, it's going to tell you. And so, yes, if you have it available, I don't hate the device. I just don't want students to solely know how to check an outlet with a plug-in tester. Right? If you don't have it, if you're in an industrial setting, you don't see these a lot in an industrial setting. There's a lot going, there's a lot of reasons why we absolutely need to know how to use our meter. All right, any extra questions around outlets? As far as these goes, we're going to move on to another set of outlets.
Yes.
Yeah, the bigger ones. So, for no reason at all, I just brought both of them. this is the 30 amp here, and this is the 50 amp. Like I said, for no reason, I could have just done all this with one, but I do want to point out that there are.
Are they upside down?
Say that again?
Are they upside down?
No, no. So that's a very good question. Upside down. So in a lot of Reddit arguments between electricians, this is upside down. And they're right. It is upside down. If you ever look at a device and you look at the back of the device, if you hold it like this and you turn the device around, all of the information is going to be upside down. So for you to actually read the information behind a device, you actually have to have the ground in the upward position. It is arguably, between folks, the ground is intended to be in the upward position. Now, this is debated. Why? Okay, so here's the reasoning. Does anybody know the reasoning behind why I would want the ground facing up?
Yeah, if you drop something, it'll hit the ground.
Excellent, very good. If something falls and it's metal, the first thing it hits is the ground. And so with this outlet, if the metal falls, it can potentially short out the circuit or, break pieces of equipment that are connected to it. So very good. That's the reason why the ground should go in the upward position. But the argument is, well, what if the device is up? Then it could be argued that we want the ground facing down, because now the circumstances might be reversed. Something might be going upward and hit the device. So, however, and this is what everyone knows who's done install in people's homes, if you install ground up, everybody's going to call you back and say, hey, you installed the outlets backwards. Everybody wants the ground down. I don't know why it became an industry standard. I don't like that 30, but it is.
I heard because it looks like a face.
Maybe, right? It has more of a what do they call that?
More aesthetically pleasing.
Yeah, more aesthetically pleasing. It's not more of a human feel to it. Like it seems like it's a person.
Smile face.
That's why we don't like to, like, if somebody yells at a room. Did you know that? Like if somebody yells at a robot, people feel that and say, hey, don't do that. If you were to yell at the Roomba, what a stupid thing. People actually, some people like, hey, don't yell at that. Which is weird, but I get it. But I do want to point out, just to verify, right? If you look at the NEMA, if we turn this around, we would be reading this in the opposite direction.
Yeah, I just couldn't see it because the lights are on.
Yeah. Oh, okay, gotcha.
Sweet.
Let us now minimize that back up. So I do want to teach you we briefly touched on this yesterday, as you had mentioned that you tested one of these and half was good and half was bad. So one of the things that we do want to make sure with these, but again, just want to teach you how to walk through testing one, is what's what here. So yeah, very good. Everybody kind of picked up on what's what here. This is the ground.
240.
There's the neutral. In a straight 50, that's the neutral. This is the ground. And then both of these are going to be hot. Now, very important that you do a double check on one of these. If you're at a breaker, then impossible to happen what I'm going to show you can happen here. Again, at a breaker, this could never be the case. But at an outlet, because somebody ran wires to this, and I don't know what these wires are, because it's behind concealed stuff, I want to do a hot to, let's just say ground, or actually neutral. We always want the neutral in play. And we want to check 120. And I'm going to put here twice, like was pointed out yesterday. If you do a hot to neutral check, sorry, let's do the neutral. And you have here, you also have to do a neutral to that hot as well, and make sure you have it there. So because there are two hots to this, we want to do the check for voltage twice. Now, yes, you're going to do this also to the ground. I'm not so much concerned right now with this setup for these. You guys get the idea. This is an outlet that we just looked at, and this is another outlet that we just looked at, so you can definitely approach it in that sense to see if the ground is here. But here's the important one. You want to do a hot to hot check. Oops, I put neutral there. Sorry. I want to check between the hot and the hot.
So you should get 240.
Exactly. I want to make sure I get 240. Because, and I have seen this happen. All right, this was wired. You always get called in because, hey, my friend or someone who said they know how to do something wired it. And what happened was the person went to the panel. They saw an open spot on the panel, and they saw another open spot on the panel. Yeah, and they did math. All right, 120 over here, 120 over there, blah, blah, blah. That's 240. Send a wire from there over here. Send a wire from here over there. Plug in the machine doesn't work. What happened is, just by luck of combination, they picked an A phase, let's say, and another A phase. And that's not going to give you 240, even though on paper, 1 plus 1 is 2. 120 plus 120 is 240. But we got to have the opposite phase here. Yeah, we have to have two different phases. Now, it is already a bad idea to separate these in two different locations. The code says both of these have to trip at the same time. Not that you can't use two singles, just that the two singles would have to be side by side. And that way I can set this up with they sell a pin that connects two breakers together. Also, you can do it with a number 12 wire, solid. And also, and the main thing is you avoid not picking up the second phase, which is the important part. All right? The second phase, two different phases have to be at these outlets. Now, if this was a three-phase system, doesn't matter as long as it's A, B, B, C, A, C, doesn't matter. But again, keep in mind that they have to be side by side, so we want a combination of side by side. All right, that's the only thing I wanted to show you guys for this. It's how to check this, check it with twice. All right, make sure you're checking between both of the points. All right, now, and as I said, we got a fairly short lecture. I only have two more things to walk you guys through. One of them is going to be tools, which I just want to show them. It's a more show and tell. You guys have seen all the tools, although I do want to get to some points about them. But last but not least, of the things that I want to make sure you guys grab as notes is short circuit calculation. All right, we got a homework with short circuit calculations. So this is what this determines. If I'm not mistaken, it was for me, and I think they still have them. This does come up in the journeyman exam, where they ask you to determine what is the potential short circuit calculation or interrupting rating of this circuit, and then they give you a circuit. So the thing that we're focused on, because we did transformers, is the transformer now. All right, this is what's going to determine whether or not, let's do a step down, because more likely than not, what this is going to look like. Now, the transformer has some information, but one of the information that we actually didn't talk about too much is the wattage capacity of the transformer. We did. I gave you guys what kVA was. So let's say this transformer has 25,000 VA, right? Again, that is a calculated measurement of wattage. Wattage is power, so VA is not power. VA is just the nominal number associated with the power. If I were measuring power, then I would be measuring in wattage or kilowatts. And then, as you guys know, there's two voltages to both of these. So let's say we have 480 on this side, and we have Let's do 240 on this side, meaning we have 120 A phase and 120 B phase. Now, when you do this calculation, and this is just a little bit extra, I'm going to be giving you the information. You guys will see it in the quiz, and we'll just look at it real quick before I let you guys go today. When you're worried about this calculation, you're not concerned with what both voltages are producing, because the short only happens on one. Technically, when we calculate it, we only calculate one. So we're actually only worried about one of the phases. This is not so important because, again, I'm going to give you the number that you're working with. But there's a little bit extra that I want to put here as far as how we call this in fancy words. In fancy word, this is E pri, right, in fancy math. And this is E sec, right, or secondary and primary. So, to do this calculation, the formula, there's going to be two parts to the formula. Part one is Ohm's law, but we write it out fancy. We go kVA over E secondary, because this is the voltage that's going to be feeding the short circuit, not this one. So E secondary determines amperage, but we call amperage here I secondary. All right, that's the fancy formula for Ohm's law. P over E equals I. All right, this is just Ohm's law all over again, as is most calculations in electrical. So let's step one this. Let's step one calculate what I secondary is. All right, can anyone give me I secondary right now?
Is it 0.2?
No, we went a little too low. Not a little, a lot too low.
4.8?
It's not points, this is a big number.
Isn't it 25 divided by, oh, I see, it's 25,000.
1,000, very good. Divided by
120, so it's 208.3.
Very good. All right, we're gonna drop let's drop the 0.3 and all that good stuff behind it. Very good, 208. All right, good. Yeah, and sometimes, by the way, sometimes I'll see the results after the quiz or the homework, where someone just, what do they call that, a brain fart?
Yeah,
I forgot that 25 kVA is 25, and I did a crazy calculation here.
Yeah.
All right, now to step two of the formula. Step two of the formula is I secondary times the constant multiplier of 100 divided by another fancy word, which is impedance percentage, represented as, they call this IZ, if you ever hear anybody talk on this, but we'll just put IZ. It means impedance percentage. The impedance percentage of the transformer is the amount of energy lost when you transfer the magnetic field from this side over to this side. Transformers don't have 100% efficiency. There is loss of energy. You can actually feel the energy loss. How do I feel the energy loss? Well, if I touch a transformer, it's being used like I said with your phone charger, plug in your phone, come back 20 minutes later, put your hand on that charger, it's hot. That's energy loss. If there was no energy loss, if your transformer was 100%, if it's your phone charger, 100% efficient, it would be coldish to the touch, almost frozen to the touch. I'll give you an example from my childhood. In my childhood, you didn't touch a light bulb that was on, or your skin stayed on it, because there was a lot of energy loss on the old incandescent light bulbs. That's why they were 100 watts or 150 watts, because it took 100 watts of energy to produce light, because we lost 90% of that energy to heat. That's why the light bulb was on fire. But now in modern times, what does an LED draw? 10 watts, 15 watts, 5 watts, so low. And guess what? You can put your hand right on a working LED and unscrew it and replace it. It is slightly hot because there is a minimal amount of energy being lost, but it's not, it's not 100% efficient, which they're working on 100% efficiency. Someone is at MIT or something like that. So all transformers have a percentage loss to them. The smaller transformers have lower percentage losses. The bigger transformers, because it's just big amount of energy transferring from one side to the other, have bigger amount of energy loss. This is information that I'm going to give you. All right, it's on the sometimes it's not even on the transformer. The manufacturer of the transformer knows it, but it's not a set of specs that they're going to put on the transformer for us. We don't need that information unless we're doing short circuit calculations. So on average, we'll just use an on average of 3.5. Now, here's what I do not want you to do in this calculation is move this decimal. Do not move the decimal. Use the actual number, 3.5. So let's finish up this calculation. All right, I'm going to put it over here to the side. 120. Sorry, not 120. We calculated 208. Multiplied by 100. Divided by 3.5. And now, the number that you guys are going to see here is the potential amperage that is going to happen during a short circuit.
So 5,942.
5,942 potential in rush of current amps, so we can say about 6,000. Sorry, I forgot the A. Amps. Now, this is an average breaker. This is an average transformer outside of somebody's house. Of course, 120 is what we have inside a house. And somewhere around 6,000 amps is what's going to rush into the average home circuit during a short circuit. This is why, when I pointed out the breaker, going back 1 second, and I'll be back to that if anyone's still writing, I said that the short circuit rating on most of your home breakers, all of your home breakers, is 10,000 kA. So that's the last note that we are going to write down today, which is, and now I'm just going to erase this math here. All right, and I'm going to put breaker interrupting rating.
Yeah.
Must be larger than short. I'm going to abbreviate this just for me, just because I'm running out of space and all that good stuff. I just want to change Stan. Short circuit calculation. You guys want to write that out? Go for it. That's the only other thing you have to know about short circuit calculations is the breaker we select must be larger, not equal to, must be larger. All right, sometimes we go equal to is good enough. No, not in this case. Must be larger than the short circuit calculation that I come up with. So let's say, for example, I came up with a short circuit calculation of 28,000 amps, then 30 amps, 30,000 or 30 kA, 35,000, 40,000, anything, as long as it's larger. Now, of course, price is going to come into effect, so they're kept fairly close to what the short circuit calculation is. But again, larger is the key, not equal to. All right, of course I am recording this so you guys will be able to see all this at the end. And now, last but not least, again, I want to just run through some troubleshooting tools. I'm going to give you notes for one of them, but other than that, Pretty standard troubleshooting tools that we have, and then we'll wrap it up. This will just be a quick visual, and if anyone has any questions, of course. This is, again, to check the circuits for problems on them. You should know how to read these pretty straightforward. It's going to tell you what good looks like and then what problems look like. This one is going to give you the hot neutral reversing, hot neutral, hot ground reversal. Now, what I want you guys to know about these two is that these are two different meters. All right, they're both digital multimeters. All right, these are both digital multimeters. But the one on the right does not check for, anyone knows what it doesn't check for?
Our right or your right?
Should be all of our rights. You should be remembering.
It doesn't check for the magnetic field.
Right, it doesn't check for amperage.
Yeah.
That this one does. Very good. So if ever, again, I like to make sure simple stuff don't get you stuck out in the field when you go work. And this would be something that would be kind of like, you know, a big red flag. If they said, hey, measure the amperage on that circuit, and you just went over and grabbed any meter, you grab that one, and you're saying, hey, how do I measure amperage with this one? They're going to look at you like, what? So we want to make sure anytime we're measuring amperage, there is a clamp on device. All right, that is the clamp on. I think you guys know the name of that, so you might not need it. And of course, and this is just a side note to this, we do want to keep that wire as close to dead center as possible. All right. If you get a little bit too high, then you might not get a very accurate reading. So we want to get the wire as dead center as possible when you're checking amperage. Now, the other thing I want to make sure everybody knows is how to read which one is AC voltage, which one is DC voltage. Usually people know these two. And sometimes this shows up.
Usually you have to select the function and make it AC.
Yeah.
Right. Sometimes you have to select the function like we have here. I have to select that one is DC. Below that is AC. But sometimes you have this one. In fact, you have it on this meter. You have it up here. Actually, I have it kind of backwards here. Straight line, squiggly line. What this is telling me is auto select. All right, some meters, my favorite meter actually for troubleshooting. I'll show you it real quick. Feel free to buy it whenever you're ready. It is the easiest meter to use. It's also expensive, but it's an easy meter to use. And let me see, I can grab one that I can zoom in a little bit on to show you guys. Yeah, here we are. This is the best troubleshooting meter that they make. All right. First of all, it's that company right there, Fluke, which is the best metering company out there. Right? This is like the Cadillac, or not Cadillac, but what is the best car now? Mercedes or something?
Bugatti.
Yeah, there we go. It's the Bugatti of meters. Like the price is going to show you that, right? This is just a digital multimeter. This is just your this doesn't even have high amperage scale. It's 200 amps, just like the one we gave you guys for school. But this is $300.
Yeah. Well,
that one up there says 500.
Mr. Perez, why doesn't it have like the clamp? You just
Exactly. The reason why it doesn't have the clamp is because you do not have to worry about getting the wire dead center.
Oh wow.
Yeah, I know. That's the price tag.
So it's kind of pay to win at that point.
Yeah, exactly. So you just and the other thing is you don't have to open and clamp and get through wires. So there's no maneuvering. I remember when I was talking about selecting amperage or trying to measure amperage on a panel.
How long have you had it?
Oh, those things last you forever.
You've had it for
that's the best
had it
one
for a
you
long
said,
time?
right?
I've had, yeah.
It made you a lot of money?
I would say it's paid off for itself. It's paid itself off completely. Yeah.
It's gonna borrow like $300.
No, but here's what you can do.
Wait, where's the school again?
2 troubleshooting side jobs at 150 apiece, and boom, now you got this. And you
What?
can attribute that to me helping you. Right, but like just real, if I'm gonna measure anything on this panel, I don't like up here. I don't have to move the wires out of the way. I just slide. It's very easy to check amperage.
I have another deal for you. How about you just let me come and fix that problem you got in your garage with that one plug that
Add a plug. All right, can you do that?
you got for
Painting.
No problem. No problem. You'll have to get out to Chattanooga, but we'd love to welcome you. I'll take you fishing when you get here. But I just wanted to show you that center. If you notice the voltage on there, it has the symbol that I'm talking about.
Yeah, it does.
Yeah, so this is an auto select. The good thing about this one is you'll notice top left, there's only 3 things that this has available. Voltage, amperage, and continuity or ohms. When you put it on ohms or you put it on continuity, it knows. It doesn't, you don't have to select through ohms and continuity. It just beeps for you and gives you the ohms at the same time. Same thing with the voltage. You put it on volt. This is why it's really good for troubleshooting in motor control settings, because a lot of times motor control circuits have different voltages throughout the actual circuit. I might be working on 480, 24 volt DC, and back and forth between AC and DC voltage. So I don't have to switch my meter up, then measure, then go over here, switch it again, measure. This is fine, but if you're in the business of doing this all the time, then remember what I said yesterday, time. We're always trying to avoid steps. All right, do not use this for voltage ever. This is a magnetic field sensing device. All right, so I will put here. By the way, this is a no contact pen. Yeah, everyone's favorite. I'm not saying don't have it. This is very good for a new electrician to have.
It's not checking. You can't read anything.
Right there, it's not going to give you a voltage reading. Not for voltage reading.
Yeah, that's all it's for. It's live. Let me check and make sure that it's live in here.
Exactly. And by the way, don't use this for the outlet. If someone says, hey, there's no power at my outlet, don't put it in there. Because it could pick up magnetic fields on neutrals. All right, it can pick up magnetic fields on any wire. So not for voltage testing. It only picks up the magnetic field. Again, if I'm opening up a junction box and I want to know, is there a wire in here that's hot? Then absolutely. Put it right there. And all right, now I got hot in there. Be careful. Circuit tracer. This one's also very useful if I have no idea what breaker is feeding the outlet. Voltage tester or tracer, is a good idea to get into. Do you need it? Maybe, maybe not. Not yet. At some point. This is the last one I do want to give you the notes for this. Yeah. Mega ohm, one word, but the best name ever. Right? Because it's just 3 words. Mega ohm meter. Now, the thing I want you to know about this is what it tests. All right, it checks ohms. All right, but not on the conductor, right? Not on the copper side, right? This checks insulation. Yeah, resistance. What this is going to tell you is if the insulation around your conductor is good or starting to wear. And this is used for high voltage systems.
It's in the motor.
Yes, it's also used for motors to check the resistance of the windings, but you guys will learn about that, next module. And the other 2 notes that I want to write around this one is low R, resistance output res, is bad. And then high resistance, this is good. Now, normally, high resistance in a circuit is bad because high resistance in a circuit means my voltage isn't flowing very nicely. But if I'm judging my insulation better have the highest resistance possible. My insulation is the thing protecting everyone from dying. So the higher the insulation rating, the better. That's why you'll see here for the megometer, we want to go into the high numbers because it's checking insulation. All right, everybody standing up. You guys are good to go. 11:17, not bad. Everybody back here tomorrow. This video will be posted in a little bit. And remember, tomorrow bring in your exam information, all the wrong answers, and we'll go over them tomorrow.